loud. All right, so we are officially recording. And now I just need to pull up the projector. Bring this over here. Screen share. So we might be running into, oh yeah, look at that. Okay, it says the camera cannot be used now. So I guess if I'm recording on Zoom, yeah. Stop my screen share. Oh, wait a sec. Oh, look at that. Okay. All right, sorry. I'm just trying to figure all the stuff out here, but I think we're in great shape now. Okay. All right, so we're going to take a look at section 10.2. So this is for first period and sixth period. And the good news is I'll put this recording in my courses, so you may not need to go back to it, but if you do for any reason, you'll be able to. Okay, section 10.2. We are looking at lines tangent to a circle. All right, so our focus today is looking at what a tangent line is and how the tangent line is related to the radius of a circle and the point of tangency. All right, so we'll talk about what all that stuff is. All right, so the first thing is understanding what a tangent line is. So a tangent line is a line in the plane of the circle that intersects the circle at exactly one point. And we call that point the point of tangency. Right, so for example, if I have a circle, okay, here's the center of the circle, I'll call it C. Right, and then maybe we have a line that is in the plane and it basically intersects with the circumference of the circle at one point. Right, I'll call that X. So right here, this X is the point of tangency. So we'll say X is the point of tangency, right? And then this would be the tangent line. Okay. And I'll label this line, I'll just call it line M. We would say line M is the tangent line to the circle. Any questions so far? All right, so if I connect the center to this point of tangency, this little segment CX is also equal to the radius, right? This is the radius of the circle, right? And of course, you can have an infinite number of radii in any circle. So I'm just going to call this CX. That segment CX equals R. And this right here represents the shortest segment from C to line M and the point of tangency. And also CX is perpendicular to line M. Okay, so CX is the shortest segment. Right, CX is perpendicular to, I'll call it line M. All right, any questions so far? I'll leave this here for just a moment. And although I'll be gone for most of the school day today, I will be back at 2. So we will still have after school geometry review. We'll still be working on some IXL, or again, some of you are coming by to finish up the test, and we'll be doing that as well, right? So it'll just be whatever you need for geometry after school today. All right, are we ready for the next page? All good? Okay. Nobody wants to talk and be preserved on a recording in my courses forever, or at least until the end of the year. I don't blame you. All right, so we're going to start out looking at a theorem. This is theorem 10.1, and we'll also look at its converse. All right, so I'll just lump those both together in theorem 10.1. Okay, and this really just kind of formalizes what we were just talking about, that if you have a segment that is a radius of a circle, well, actually, no, this is the line. You have a line with a tangent line to a circle. The radius is going to form a perpendicular with that line. Okay, so I'm going to change the notation. We'll make that line AB instead of line segment. So if line AB is tangent to circle C at some point P, then that means line AB is perpendicular to P. Okay, it looks like this. Right. I'm going to put the tangent line up here this time, right? It can be in, pretty much it can be anywhere in the circle. It can be here, it can be here. All right, so this is AB. This is circle C. All right, and so this tangent line is perpendicular at point P, right? Meaning it forms right angles. Okay, and the converse, again, that's just saying the same statement backwards, right? So if AB is tangent to circle C at point P, then AB is perpendicular to P. The converse is just saying if line AB is perpendicular to P, then AB is tangent to circle C at point P. All right, so pretty straightforward. Right, any questions? All right, so let's work out an example and see how these are used in solving problems. All right, so here's my circle R. And here is ST. And then, let's see, draw it like this and like this. Okay, so right here we have our segment ST. And I made that segment a little longer than I needed to, so let me go ahead and just erase that part. There you go.
Are you going to give this the hypotenuse so that you just divide it by 2 and then you get the radius?
Definitely giving the hypotenuse right here. Okay. Perfect. Now,
Is 9.
radius is a little bit different.
How?
So this one, so this is not necessarily a special right triangle, right? Because you're thinking like, I know exactly what you're thinking with the 30, 60, 90. And then you're right, that would definitely be 9. I agree. In this case, it's not necessarily, it doesn't have to be a special right triangle. So what we do is as long as we have 2 of the 3 side lengths, we can just plug it into the Pythagorean theorem. So we want to know what is the radius. And let's see. So we do a squared plus b squared equals c squared. I'll just make a little note. We're using the Pythagorean theorem. All right, so then I'll let the radius be a squared. It doesn't really matter. I can let it be a squared or b squared. What matters is that c squared is always the hypotenuse. All right, so a squared plus 24 squared equals 18 squared. All right. This is my batteries. Okay. All right, so I'm going to work out 24 squared. Gives me 576. So a squared plus 576 equals, wait, that's kind of weird.
Why is the hypotenuse shorter?
Ah, I know why. I know why. I have to add an extra note here. This 18 is only good up until this point. Okay, so the 18 is not all of this. So if this is 18 and our radius is unknown, then we have to add the length of the unknown radius to this. Okay, so I don't know what the radius is. I'm just going to call it x. So we'll say 18 plus x squared. Okay, so right here, 18 plus x, and then we square it. All right, so all of a sudden this becomes more of an algebra problem. A squared plus 576 equals 18 plus x times 18 plus x. All right, and then on the right side, we have to FOIL it out. Okay, so I'm going to multiply 18 by 18, that's 324. 18 times x, that's plus 18x. And then right here, plus 18x again, multiplying the inner terms. In our last terms, we get plus x squared. Set that all equal to a squared plus 576. Okay, and what I'm going to do is make a substitution. I'm going to let a squared equal x squared. And the reason I can do that is that on the Pythagorean theorem, this side a is also the length of the radius. So then I can write it as x squared plus 576 equals 324 plus, and then we'll just add these two like terms, 36x plus x squared. All right, what can I cancel out on both sides?
X squared.
The x squared, exactly. Yep, those can go. All right, so then,
24 for both sides.
exactly, yeah, so we subtract 324, 324, okay. So then, it's gonna be 252 equals 36x. And we divide,
36.
yeah, divide by 36. Radius length is 7. All right, so using the Pythagorean theorem, but also having to do a little bit of critical thinking, understanding that this 18 only goes with this piece, this radius x's are unknown. Any questions about how we solve that one? Good. All right, let me leave this here for a minute.
Will we ever be given a 3069 because I would just make this a lot simpler.
It would make it so much simpler. It would make it so much nicer. Maybe, maybe not.
We should sneak one onto the test and see if anyone notices.
You know what? That sounds reasonable. Right? Sounds reasonable that we put one on here. Because I mean, you could, right? Because this angle, right? This right here, R to T, this could be really any angle less than 90 degrees. Yeah, I'll take that into consideration. Would anybody like more time here? All good? Okay. So on to the next page. Let's see how much we've got left. All right, so I've got another theorem for you. Oh, we don't have much left at all. Okay. I'm going to give you another theorem and then a couple of examples, and we will call it a day. Okay. So this is theorem 10-2. All right, and this is the segments tangent to a circle theorem. Okay. According to this theorem, if you have two segments with a common endpoint exterior to a circle that are tangent to the circle, right? So if you have something like this, I'll let this be point P. This will be C, which is my center. All right, and let's say I have these two segments that are exterior to the circle, right? Meeting at this one point. Okay, they meet at a point exterior to the circle, and they're tangent, so they each have a point of tangency on the circle. What that means is that these segments will be congruent or the same length. Okay. Okay, and from the previous theorem, we also know that they'll form a 90-degree angle at the point of tangency. All right, so here we could say Let's see, let me go ahead and, well, all right, I'm not going to get ahead of myself. Let me just call this A and B. All right, and we can say here that CA is congruent to CB. You might see an example like this one. You may be asked to solve for an unknown. Or maybe you have your circle right here. You have your tangent lines meeting here and here. All right, my drawing's not the greatest, but all right, let's call this segment 2x plus 12, and we'll call this one 3x. Okay, so since we know that these segments are congruent, how do we solve? Right, if they're congruent or the same measure, what do we do?
Oh, x equals 12. Because they're congruent.
X does equal 12, yep. So right here, since they're congruent, that means you can just set them equal to each other and solve for the variable. So we can say 2x plus 12 equals 3x, right? And then just subtract 2x on both sides. 12 equals x, or x equals 12. All right, very good. So let me know if you have any questions there. Great, and then I have one more example for you. Let's see if I can fit it on the bottom of the page here, maybe. Okay, so for this one, we want to find, we want to solve for x. We have a diagram that looks like this one here. Okay, so I'm going to call this circle T. And I've got my tangent lines here and here. Okay, they meet right here at point A. This will be point B and point C. Okay. Then we have this here and here. Okay, and remember, we know that the tangent line is going to form a right angle with the radius. So we've got two right angles here and here. Okay, this is x degrees. And then this angle right here, it's not really drawn the greatest, but this central angle here is 135 degrees. All right, so how can we figure out the value of x? What do you think? Could we get away with saying, and I do want to make this more of an angle here. Could we call this a quadrilateral with 4 sides? What do you think? I've got a side here, here, and here. Yeah, quadrilateral, right? Yeah. Okay. What's the sum of all 4 angles in a quadrilateral? Right, we know the triangle's 180. What's the 4-sided figure? 360, perfect. All right, so if we know that the sum of the four angles add up to 360, then we're just going to take 360 and we're going to subtract out 135 and then the two 90-degree angles. All right, excellent. Okay, so equals 360 degrees. So that means that 360 minus 135 minus the two 90-degree angles, right? We just worked that all out. And then that would equal, let's see, it'd be 180 minus 135. So angle X is 45 degrees. Oh gosh, it did the zoom again. I didn't know, I'm sorry. All right, there we go. All right, so angle X would equal 45 degrees. So I'll leave that there for a moment. Let me know if you have any questions.
Miss Kelly.
Yeah.
I feel like that was overconfident.
It was a little bit roundabout, right? So yeah, sometimes when we're looking at certain theorems or certain sections, we might be solving from a different perspective. But yeah, you could totally look at this and just be like, oh wait, just subtract these away from the 360 and you're good.
Am I allowed to do that on the test?
Yeah, as long as you show how you did it. Yeah. All right, so I'm going to go ahead and end the screen share. I am going to stop the Zoom recording for my 6th period folks here. Let's see. All right, end meeting. I do hope this worked.
There's a share button.
Yeah, I want to, so I ended the share. Now what I think is strange is it's showing that I need to sign in, but I was already signed in, so.